All right, so thank you very much. I would like to start by thanking the organizers for giving me this opportunity to talk here today. I've put this somewhat provocative title here for my talk. I would like to start by first thanking my PhD student Ramanujan, who's done the most of the work in this underlying this presentation. And the paper is highlighted in the yellow box if you want to look at the details later on. And also Andrew Grosek, who is currently a postdoc at the University of Queensland. And I would also like to thank Australian Research Council, who is supporting my research for many years now. All right, so actually at this point, I would just like to mention that I'm not going to be able to see any, well, currently I don't see any questions or anything like that. So if there's, I'll just keep talking and assume that if there's any questions or so on, you will alert me of that maybe at the end of the talk. All right, so the outline of the talk is I'll start with the motivation and then I'll go through the key results that I want to share today and then finish off with the conclusions. So I will begin by a statement, and I read it aloud, even though you can read it as well. So I'm making a statement that driven systems tend to self-organize. And you can find an awfully many examples of this statement verifying its truth value. If you scour the internet, for example, there was today's first talk also showed a beautiful example of self-organization in a driven system. And I've put in here just the three examples to add to that list. So, for example, the first one here is a swimming bacteria in a petri dish. These are self-propelling little microorganisms that are driving the system themselves and form these self-organized vortex structures, very much looking similar to the vortex structures we see in 2D quantum turbulence, for example, in these confined spaces. And the second one is the well-known scenario of flocking birds. There's plenty of videos and images online that you can look up if you haven't seen them before. Very beautiful pattern formation taking place there in these driven systems, sort of kind of active matter systems, what they're called these days. And then finally, obviously life itself. The system takes energy from the sun and produces unbelievably amazing patterns and structures ranging from plants to human beings and so on. So this is the starting point that we expect to see these sort of self-organized structures emerging when the system is being driven. And those systems take some of the energy that goes into the driving and consume that energy. Some systems feed it back. Some systems could potentially use all of it and just produce heat. But very often we observe a scenario where this at least some of this energy is consumed to reduce the entropy of the system. That is, the system does work in order to create these organized, ordered structures. Now, turbulence itself, on the other hand, usually the way we think about it is exactly the opposite. We think about a turbulence as something completely disordered and disorganized and the maximum mess that you can have that could potentially, could not have any kind of structure in it. That's at least a sort of a layperson's view of what turbulence is. On the other hand, we also know very well the picture of the Paulo scalings that spectrally emerge in these driven turbulent fluids and systems. But that then means that there has to be some sort of actually very particular kinds of correlations within the turbulence. So in order to observe these turbulent Kolmogorov spectral cascades, there has to be some sort of underlying ordering in these systems, and I've put it in this cartoon way where you see the Richardson cascade shown in this cartoon way with these loops. And if you look at that picture, then of course immediately your brain goes into thinking of ordered structures rather than something that is completely chaotic. So the question there then is, would it be possible that turbulence actually could be some sort of an ordered state when viewed in from some suitable space, maybe some abstract space, not in the usual velocity and momentum, velocity and position parameters, but maybe some abstract space. And I'm putting here quasicrystals as an example, where quasicrystals themselves in our usual real space presentation don't have any long-range order whatsoever. But on the other hand, there's a representation of some higher dimensional system where you take a perfect crystal in some high dimension, and then you project it down to the, let's say, in our 3D space or 2D, and then you observe these quasicrystalline structures in this lower dimensional space. So that points to the idea that maybe something similar could potentially be going on with turbulence. So with those motivational words, let's now dwell into something a little bit more concrete and something that we can actually grasp a little bit easier. And so we go back to the usual 2D quantum turbulence picture, and you see the movie there. Many of you have seen this before, where we are looking at blue and green vortices, plus and minus sign vortices, doing their dance in this 2D quantum turbulent fluid, Bose-Einstein condensate. So what do you see there is of course initially this big mess that we associate with turbulence, but at the end of the movie, you start seeing these ordered Onsager vortex clusters, the blue cluster and the green cluster emerging. So at least in some sense, we already know that in this particular type of turbulence, we do see ordered structures. But these ordered structures emerge at the end of the cascade. So in some sense, they are not actually part of they're definitely not part of the inertial range as such. They emerge at the terminal point of the cascade. And even though we can visually see them quite easily and identify them even just by looking at these movies, the question really is that could something similar take place also in the inertial range? And just by looking at this movie at early times, it is quite easy to see that it's almost impossible to imagine that there would be some ordered structures that would be characterizing the turbulence in those early times in these movies. However, we also very well know that the AI has got better eyes than we human beings have in many cases, well, at least in some cases. So the question then arises, would it be possible to use AI techniques, machine learning in particular, to identify some subtle correlations in these turbulent flows that we would not otherwise be able to identify? So in order to explore this idea further, we start with the most simplest scenario imaginable, with two vortices only. So here in the top left corner, you can see figure A, where we've got two vortices, the green vortex and the blue vortex. They are actually the same sign. They're just colored with two different colors. And in figure B, you see the dynamics. So if we evolve this initial configuration in time, the two vortices just travel along these circular paths. And in figure C, the same simulation is viewed now in a different perspective, where we are plotting the angular velocity as a function of the radial velocity of these vortices, and we see these two loops emerging in this case. The second row is the same thing. The only difference here is we start from a slightly different initial configuration where the two vortices are just a little bit closer to each other. And if you compare the figure A and D, there's not a lot that you can say that there's difference. It's not very easy to say anything more than that, okay, the other case, the vortices are closer, and the other case, they are further apart. But the dynamics is drastically different. So in one case, the phase space is doubly connected, and in the other case, it is singly connected or doubly and triply connected, depending how you want to view it. So the ergodicity is broken in this dynamics, and in one case, the two vortices travel along their independent paths, and in the other case, their phase space paths or real space paths are overlapping. And this becomes very easy to see in this velocity plot diagram in the last column, where either we've got two loops or just one loop in these images. Now, what we then do is we create thousands of different kinds of initial configurations, placing these two vortices in randomly all over the place in this 2D system. And so in the bottom row, there's the corresponding each of those columns. So the red dots and the blue dots are every single dot is one initial configuration or one image, one simulation. And what we've done is we've taken these thousands of images and fed them into the machine learning algorithm. And the machine learning algorithm outputs two categories, the red category and the blue category. And if you look at the figure I, for example, you can see the black curve there is actually an analytical solution that separates these two kinds of behaviors where the vortices travel in overlapping paths or they travel along separated paths. And we can see that the red and the blue dots are beautifully agreeing with the analytical result. Now that might be, at the outset, it looks like, well, that's maybe not so surprising. Anybody can look at these velocity plots and categorize them into single loops and two loop figures. So maybe that's not a big deal. And the same goes for the middle column, where also the vortices in the real space are traveling either in a sort of a single donut or two separate circles. And you would imagine that it would be easy to classify these as well. And the figure H shows how the machine learning does and perform very well in this case as well. The most surprising thing is the first column, where you can now imagine if you put these two vortices in random locations there, I don't think there would be any way for human eye to recognize, classify these into two different categories purely based on the initial configuration without seeing anything about the dynamics. Yet we still get pretty good agreement in the machine learning outcome of classifying these two different dynamics. So this gives us some hope that maybe this idea might work more generally as well. So this prompted us to go into obviously to larger numbers of vortices, and here you can see an experimental image of a vortex configuration in a BC. And so the procedure here would be, of course, you would collect large number of experimental images like this, and then you would identify the locations of these vortices. And by the way, these days, of course, people are doing this also using AI rather than having somebody clicking a mouse to find where those dots are. So these vortices can be actually, the locations can be also identified from the experimental images automatically using AI techniques. And then you reduce the images into these sort of low-dimensional point vortex configurations. Now, instead of taking thousands and thousands of experimental images, it sort of makes sense to first try this theoretically. So what we do is we just use the point vortex model to produce these configurations tens of thousands of vortex configurations with different energies. The Hamiltonian, point vortex Hamiltonian is there. That gives us the energy of the system. We can evolve these initial configurations to get the dynamics. But what we've done here is we've used the Monte Carlo technique to basically characterize different configurations, vortex configurations, in terms of one parameter only, the point vortex temperature TV in this Boltzmann factor here. So here's an example of this procedure. So we've taken 30,000 different vortex configurations across the whole range of energies possible in this system, and we fed these images, as you can see here in these 4 different square boxes. We've fed all of these images into this machine model, and the machine model has spat out 4 categories for us: a yellow category, green category, blue category, and red category. And as you can see, if you look at the red category, for example, it's quite easy to see that, okay, yes, I can see that all these images there have got some similarity. They all have got this cluster of vortices in the sort of middle of this image. And likewise, in the yellow category, you can see that the vortices form sort of a edge mode at the boundary of the system. That's where they've collected. But if you look at the green and the blue, you can already start seeing that it wouldn't be very easy for you to distinguish, given one of those images, that whether you should place it into the blue basket or the green basket. So that's quite interesting. And then if we actually go further and quantify this, as we can do by plotting these, for example, in figure A here, the x-axis is the inverse vortex temperature that we have a direct access because we've produced the initial configurations using the Monte Carlo method. So we know for every image, we know exactly what the vortex temperature is. So we can plot it on the x-axis, and we can extract the angular momentum or the moment of inertia of these vortex configurations on the vertical axis, and we can plot them here on this graph. And what we see here is the color coding of the yellow, green, blue, and red categories. And so this is very, very exciting. So first of all, what we see is that the machine model is able to distinguish between the positive and negative temperature vortex configurations to start with. That is the boundary between the green and the blue data at infinite vortex temperature. But in addition to that, it is also able to identify the Kostelis-Thouless transition, which is the transition between the yellow and the green, and also the transition to the Einstein-Bose condensate of the Onsager vortices that is characterized between the blue and the red categories. So what we learned from this exercise is that this machine model, and an important aspect here is this is unsupervised machine model. So we have not done any training whatsoever. We literally just took all the images and fed them into this machine model, asked for 4 categories, and it spits out all these 4 categories, and each of these categories corresponds to a different vortex phase of matter. So what we have done is we haven't done. The machine model did this. The machine model discovered the 4 different vortex phases of matter purely just by using the large data set of configurations. Now, at this point, you're certainly wondering, well, okay, so you were asking for 4 categories. So how did you decide to ask for 4 categories? What if, how do you know a priori that there should be 4 different phases rather than 75, for example? And the very nice thing about this is that we can actually also obtain that information automatically without any human intervention by measuring the so-called silhouette coefficient that characterizes the goodness of this classification. So on the x-axis here, we have actually tried 10 different cases, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so requesting different number of classes or categories. And we find that the silhouette coefficient peaks up at number 4, which is an indication that the best sorting or best number of different categories for this data set is 4. And so based on that, we can run this first and then find, okay, let's ask for 4 categories, and then we can go back to the previous results and find those different vortex phases that way. The next thing is, of course, to go into the neutral vortex configurations, where a whole new issue arises, namely the fact that we now have got both vortices and anti-vortices, and in some sense this is really the case of turbulence in these 2D systems, where the turbulent flow obviously has got both plus and minus vortices all over the place. Even in this case, you see the red category is quite obvious for anyone to identify just by looking at the images, even though I doubt anyone would like to go through 30,000 images and sort them into these categories. But it is easy to see those on-cycle vortices, the blue and the green clusters there. Whereas the yellow, the green, and the blue categories now are all looking pretty much the same. So would be quite a difficult task to try to identify for any given random configuration whether we should place it in the green, blue, or yellow category here. And the same thing, we can test this, and we can also find that equally well the 4 phases are found in the case of the neutral vortex system by the machine model. So it works just as well as in the case of single sign polarized vortex gas. One point to mention here, of course, is that if you are very observant, you have noticed that these images that we are feeding into this machine model does actually include the sign information in the form of the color of the vortices. So the blue and the green vortices correspond to different signs of the vortices. So the machine model actually knows which vortices are plus vortices and which vortices are minus ones. And this information, of course, in real experimental systems is not always so easy to obtain, even though we now have ways of also extracting the phase information from the superfluid BC imagery as well. And the same story, once again, we can find that the number of clusters or categories is 4 that we should be asking for, and that's what we have done here. But getting back to the question of the vortex sign, this is perhaps the most surprising aspect of all of this. We then hid the information of the vortex sign. So we took exactly the same data as on the previous case, but instead of feeding those images with blue and green vortices, we color-coded all the vortices, irrespective of their sign, with the one single color only, meaning that the machine model had no information whatsoever on the vortex signs. And even in that case, it's able to do almost equally well. There's very little difference. So if you look at the top row, A and B correspond to the case where we've used either included the sign information or did not include the sign information. And if you look at these graphs, you can quite easily see that they look very, very similar, very little difference. Just to mention what you're actually looking at there, and to feed in also how we were plotting the previous plots. For example, the bottom row here, where you see those graphs color-coded in yellow, green, blue, and red. How do we choose at given vortex temperature which color to use there? Well, the top row shows you how we do that. So at any given vortex temperature, we've got an ensemble of, let's say, 1,000 vortices, 1,000 images, 1,000 simulations, 1,000 initial configurations for vortices. And all of those have been categorized or classified by the machine learning model into these 4 different categories. And at every given temperature point here, we are plotting the percentage of those images that belong in the different 4 different categories. And then we take the majority vote. So at any given inverse vortex temperature, we look at the which of these 4 categories is the most prevalent in the ensemble of these images at this temperature, and that determines the color coding in the bottom row images. But the take-home message here is that even without the sign information, these machine models work extremely well for this particular case. So, getting to the conclusions, what we have done is we have used these machine learning methods, in particular unsupervised machine learning methods, to sort out vortex configurations into different categories. So we take a huge number of images and we just feed all of those into the system without any training, and the system spits out these different categories. And what we have found out is that the machine model is successfully able to discover these different phases of vortex matter. Of course, in this case, we actually know this beforehand because we have studied these systems very, very long time, and we understand those systems and we know what those vortex phases are. But of course, the computer didn't know this. So in that sense, that they actually did the discovery all by themselves without any help from us. And this then leads to the last and the final point that also links to the motivation of this talk, the motivation part, which is to ask, now that we've got these emerging new technologies, AI is developing fast, and we've got huge number crunching capabilities now, supercomputers. Would there be a possibility to use these technologies to discover something new about the turbulence? In other words, could they potentially give us a new viewpoint or new perspective into how to tackle the problem of turbulence? And in particular, to identify if there's some hidden or subtle ordered structures lurking behind the turbulent flows that we normally think about in terms of this crazy, chaotic mess. And with these thoughts, I'm thanking you for your attention.
So, thank you so much, Tapio. Question? Alessandra.
Hi, Tapio. Very nice talk. Thank you. So I have a question. I'm quite new to machine learning. So in unsupervised learning, do you have a cost function that you minimize in any case? And the second question is, if you try to start from dipoles, not from random configurations, but from dipoles in the system, and then have the machine learning towards the final cluster states. And also, I wonder why, if you can have a feeling why you need 4 categories. I would expect just 2, so the random and the organized, but maybe because they are close to the 0 beta range, maybe they need more. I don't know, just wonder if you can understand it better. Thanks.
Okay, thank you. Let me start by the reverse order answering these things. So the question, why 4 categories? So that's sort of fairly simple to understand. So we've got these configurations can be split into 2. We can split them into the positive temperature and the negative temperature configurations. And so that splits, obviously, that's why we would have 2 categories. But within each of those regions, the positive temperatures and the negative temperatures, we've got a phase transition. that separates that phase into two. So that gives us 4 cases. So there's the positive temperature phase transition between the normal phase and the Kosterlitz-Thouless phase. So that's two categories. And likewise, on the negative temperature side, we also have got the phase transition to the Onsager vortex clusters and the normal phase, if you like. So that's why we have got the 4 different categories. And really, the positive temperature and the negative temperature. So the near infinite temperature, the green and the blue categories, they do have different correlations between the vortex positions, depending on whether the vortex temperature is positive or negative. So that's sort of an explanation why we get four categories. And I probably forgot already what the other questions were. There was a question on the vortex dipoles. So if we were doing the same thing with vortex dipoles, I forgot what the details of that question was.
Not a single dipole, many dipoles in the initial conditions.
I see. Well, they are actually included. So if you look at the yellow category here, these are actually vortex dipoles. So if you look very carefully, that they are within the Kosterlitz-Thouless phase, where there's only all the green and the blue vortices are paired up. So they are very, very tightly bound vortex dipoles indeed in that case, and they indeed are forming the yellow category or the yellow phase, if you like, the Kosterlitz-Thouless phase.
Okay, we have time for another question.
Hi, Tapio. It's Haida Salman here. Thanks for the nice talk. So, I don't know much about machine learning myself also, but I'm just curious, what it takes to present a well-defined problem for machine learning. So, as an example, you might have dynamics of vortices, and you're trying to back out the actual underlying model. And yesterday we had a talk from Ashton Bradley, who was saying on certain conditions you might have a dissipative vortex model as opposed to a purely conservative vortex model. If you really have no information about what's the underlying model, can machine learning help you back out this information, or do you need to put some constraints to provide it with a well-defined problem? Because that's something that's always ambiguous for me.
Thank you. That's a very good question. So let me first put it this way, that I use this as an example, this image that you're looking at here, and I think that very nicely captures one of the major issues about all the machine learning models or using machine learning to do anything pretty much, which is the question is what is the information that you actually feed to the machine model? And here's one single physical system that is the two vortices, but we have generated 3 different views, like 3 different images of the same thing. They are just, in one case, there's just 2 points, which is the initial configuration. The second case shows where do these evolve as a function of time, and the last one is yet another representation of the same data. They all, this is a Hamiltonian system, so everything is that there's one-to-one correspondence to each of these representations. But how do you choose what is the right and the correct information to feed into the machine model is one major thing. So in other words, if you've got some experimental data, what sort of post-processing do you do to the experimental data before you feed it into the machine model? That's a huge question, and it's not obvious at all, because depending on what you feed in, you might get actually different answers. Some might work, some might not. And the second question, well, more closely to what you were asking, like how would you be able to identify whether the underlying mathematical model is, for example, dissipative or not? And I would say that goes even beyond the next level, you are asking about the actual, dynamical details of the model itself. Here, what we've done is essentially we've been able to identify these well-defined phases. It's like solid and liquid, if you like, from the other. But it doesn't actually matter in that case whether the solid is dissipative or super solid, and whether the liquid is a superfluid or classical dissipative fluid. We have only been able to identify it's either solid or liquid. But if you want to go to a finer grained questions like, okay, what is the actual details of the underlying model, then of course it gets ever more complicated, and I don't really have a answer to how would you go about that at this point.
And it's that latter point that's probably more relevant to the question of whether AI can teach us something about turbulence. So would you agree with that?
Well, my point there was what I was trying to put out there is that we've got our traditional tools, analytic tools and numerical tools, and we are typically looking at turbulence from the point of view of looking at particles and their position and velocities, and trying to extract from the velocity field some information and various different things. But obviously nobody's going to go and look at the individual molecules in a turbulent flow, and you do PIV and all sorts of stuff like that. But maybe that's not the right space to look at things. Maybe the right space we need to do some transformation to a different basis. Like we need a good basis to look at the problem of turbulence, but we've got no idea what it might be. It might be some crazy, completely abstract space that would be completely meaningless to us to even think about. But these machine learning models just take the data as it is and distill the correlations in those images in a way that might actually give us insights in a completely different way of looking at these turbulence problems, rather than actually giving us the actual equation that we are needing.
So, thank you so much. I think that it's time to go to the coffee break. Let's thank Tapio and all the speakers again.